seen the demo that he gave yesterday, and he will go into more detail about the story of that demo today.
Right. Good afternoon, everybody. Thanks, Tom, for the introduction. Today, I'm going to talk to you about how we are trying to get robots to use shared elevator with us humans. This is joint work together with my colleagues at NLE, Tommaso, Jutta, Gianluca, and Danilo. Okay. Works. So, while the promotional video plays out, I'm going to briefly motivate why we are doing research in social navigation here at NLE. As you can see, we have a fleet of robots running around in a high-rise building in South Korea. And while doing so, they meet many people doing their own job, and therefore we want them to be socially acceptable while navigating. And for this reason, we do research on, for example, what's the best sound the robot should do while navigating, how can the robot, for example, leverage the interaction to solve blocking navigation blocks, and the focus of this topic, how can the robot take the elevator with us? So unless you're using this sort of medieval contraptions called paternoster lifts, usually taking the elevator is quite a non-event. It requires minimal interaction. You just enter in the elevator lobby, you maybe call the elevator with the commands if nobody did it before you, and then you just wait there until the car comes. And therefore, for our robots, we decided to go for a similar design choice. We wanted the robot to be intentionally not interactive, because that's the nature of the activity the people are doing in the elevator lobby. And this is by far not the only way we can have robots take the elevator. There are even commercially available robots that do deliveries in hotels, and they usually park themselves in front of the elevator lobby, in the elevator door, sorry, and they verbally communicate, please let me in, I need to board the elevator. But here, what we are doing is we are designing for repeated encounters. We imagine the robots to share your workspace with you. Maybe there are many robots in the same building. And if we believe that if you constantly meet these rude robots that just shout and don't comply with the social norms that we adopt in the elevator lobby, it would get old pretty quickly. So what we did was instead to run ethnographic studies and Wizard of Oz studies of how people take the elevator in real life with and without robots. And what we observed was a variety of positioning strategies and well-timed gestures that people use to convey their will to board the elevator, to yield priorities to the other bystanders, and we summarized them in social norms. And then what we wanted to do, the next step was, okay, now how do we put them in the robot? Considering, of course, the limitations that robots have. Robots don't have usually the same embodiment that we have. They don't have the same sensing capabilities. They don't have the same actuation. And the question became, okay, respecting the limitations, how can we create a smooth interaction only by using positioning and well-timed gesture as we humans do in an elevator lobby? In this talk, I'm gonna focus on the positioning. And when I talk about positioning, what I mean is something like that. This is a top view of a stylized elevator lobby. And what we want to find is places for the robots to wait in the elevator lobby that are socially acceptable, but also they can convey the urgency of the robot during its mission. For example, if the robot is willing to yield to the human bystanders, or if it's in a rush and it wants to take priority. As I said, we came up, or well, Tom, the sociologist and the rest of the team came up with a list of social norms that we respect in the elevator lobby. We have the usual suspects respect proxemics, don't stand behind people because, well, that's creepy. We also have elevator-related stuff, like elevator-specific stuff, like you don't want to stay in front of the elevator doors. That's where people want to get out when they get out of the elevator. Don't block access to the commands of the elevator. We have also observed the concept of transactional spaces. Transactional spaces is a space that is created between you, the bystanders, and the focus of attention where you are engaging in an activity. Imagine you are watching the TV. The space between you and the TV, it's a transactional space. And usually breaches of the transactional space are considered rude and should be avoided. And in the case of the elevator, the transactional space is between you, the crowd, and the focus of attention, which is the elevator doors. And last, we observed that people tend to wait as far as the furthest person when they enter the elevator lobby. This is sort of like a queuing mechanism to be expected. But I had to put this somehow in the robot. So I took inspiration of how we usually do things in navigation, and what I did was to operationalize these social norms into cost maps. So this is an example of the respect proxemics norm. And as you can see, we're having red areas that are close to the people, that are penalized, and the robot should avoid them, ideally. And this area can be made stronger or weaker just by changing a parameter. So we did this for all the other norms. Some have parameters, some have not, some were more complicated. And this was really an iterative process between me and the rest of the team. As an example, this was the first version of the wait as far as the furthest person guideline. That was easy peasy for me, like, okay, it's just Euclidean distance, you penalize everything in between, done. Well, no. Apparently, queuing has a sort of directionality, and we also want to penalize a bit the sides of the elevator lobby. Okay, so iterative process. We operationalize, we put them all together, and usually what happened is that the robot would enter in the elevator lobby and wait where it entered. Because as it turns out, staying as far away as possible from people is usually respecting the social norms. So we had to add extra social norms. These are the three we came up with. The first one was to board as fast as possible, because if the robot takes ages to board, it's ruining the service that the robot is carrying out, but at the same time, it's also you're ruining the experience for the people. You're wasting my time, basically. We want the robot to wait in areas where you can see the inside of the car, because it has to quickly decide, okay, the car is empty, I will be able to board, versus the car is full, I'm gonna board mission. And finally, we don't want the robot to collide with people, with walls and people, of course. Again, we put them together and we said, okay, let's respect them all. And usually what happened is that there was no candidate position for the robot respecting all the norms. And this was, in hindsight, kind of to be expected, because some of the norms that we operationalized, they counter each other. Ideally, you would wait in front of the elevator so that you can see perfectly what's inside, but you don't want to wait in front of the elevator because that's where people are gonna get out of it. And also, respecting an average of the norms usually yielded suboptimal waiting areas, because the robot would respect somehow all the norms a bit, but respecting a norm a bit is usually not respecting it. So, what we did here, but as human, we managed somehow to take the elevator. It's kind of like seamlessly. Even if I'm presenting the social norms as some commandments of some religion, it turns out that people are very good at just dropping some of them if the situation requires, adjusting them based on the number of people, based on the shape of the space around them. And here we had a dilemma. We could have spent more time trying to model the interaction between the different norms, model how the amount of people in the lobby influences certain norms. But on the other hand, we also wanted at some point these norms to generalize and all the infrastructure we build around them to generalize to new situations. Like it's not just the elevator lobby, it's badge gates, any threshold crossing, corridor crossing. So maybe some of you already guessed it, we turned to machine learning. And here the trick was, can we find something minimal that will transform the social norms we engineered into what we want, that is these areas. And here the problem became that we really didn't have unlabeled data about this situation, and the labeling costs were pretty high. Before somebody raises the hand, it's like, oh, there are tons of videos in the internet of people taking the elevator. Yes, there are tons of videos as such, but we argue that the embodiment and the sensing capabilities and acting capability of robots are different, and therefore just learning from demonstration from how humans act is not enough. So to overcome these issues, what we did was to procedurally generate unlabeled data, label it with experts that are familiar with how elevator lobbies work, but also the robot works, and then focused as much as possible on data frugal models, like you will see. Very briefly on procedural generation, actually it was mentioned briefly this morning just with another name, but it's kind of the same thing. Procedural generation is the creation of content using quasi-random processes, usually automated and not by hand from a person. And how it works is that you provide rules of what you want, and then you let the computer generate randomly within those rules, like while respecting those rules. And this has been used a lot in the content industry. If you have seen armies in movies after The Lord of the Rings, they all use the same algorithm to generate the crowds. It's called Massive. Video game industry, generating maps that make sense. And recently also in machine learning. Here you can see procedurally generated apartment that were used to train robots to do household chores. So that's exactly what we did in a very simple fashion. We collected maps, we collected rules of how people form F formations, like groups that make sense, rules about elevator sizes, rules about where usually the commands of the elevators are. And then we use a simple procedure generation algorithm called rejection sampling, and this is what we got. These are like top views of elevator lobbies with different amount of people, different sizes of elevators, different configurations of the space that are all right. If you start looking at them by one, you may find something that is odd, but again, we really were working without data, so that's enough for us. And while after the problem of unlabeled data was solved, then we labeled the data with experts. I will come back to this later, but it was a costly process. And then we finally went to the machine learning. Okay, how do we go from the scene you see at the top left to the segmented waiting areas to the top right? As I said segmented, I already hinted of what's the problem. That's a multi-label segmentation problem. And as you have seen it likely in the medical domain, where you have, for example, an RGB image of some tissue and you want to segment out white cells, for example. Or you have an aerial view, satellite view, and you want to segment out forest out of residential areas. And the king model for this kind of applications is the UNet. The UNet is an extremely old model. It's from 2015, which is ages ago in machine learning. But it works very well, and it works extremely well for our case, because as for the medical domain, where it was initially used, we didn't have much data, so that was perfect for us. So that's the pipeline for the training. What we had was the waiting scene based on the simulation of the localization of the robot, based on the sensing of the robot of the people detection. We can generate our social cost maps. We squeeze them as channels of an hyperspectral image, and then we feed them to a modified version of the UNet, way smaller because, again, we are working with limited data. And what we get in output, ideally, is the segmented, socially acceptable area. And we did so by aligning it to expert annotation. We collected only 125 waiting scenes annotated by expert on the two robot intentions, the taking priority and yielding priority. And this was rather expensive, not only because the expert had to be trained on what's the robot capabilities and how do people wait in an elevator scene, but also it took time. It took 2 minutes per annotation, and that's quite a lot. So before I jump to the results, I'm gonna hopefully show you a demo video, which I might need to click. Okay, awesome, perfect, it works. That's how it works in real life. Some of you have seen it yesterday. The robot is sensing the people through LiDAR and the camera that are on the front of the robot. It's computing the social norms that you can see at the bottom, putting them together through the cost map, and then we sample poses in these waiting areas, and the robot will soon, I think, navigate towards them. Here is happening very slowly because I have to explain over it, but in reality, it can happen in the moment it enters the elevator lobby. That's another demo. It, of course, doesn't work only for 1 person or 2 person. It works okay also when there are more people. Of course, if the space becomes very crowded, that's a limitation of the navigation pipeline. So as you can see, it works okay. But how well does it work? Well, here has a main metric for evaluating our model. We use the Jacquard index, or intersection over union metric. And basically what it operationalizes is that we measure how much the expert and the model areas overlap. So in an ideal world, we have 1 Jacquard index, the areas perfectly overlap. If we have 0 Jacquard index, they don't overlap, and we didn't do a good job. And to give you a feeling of what this number mean, here are a bunch of examples with different Jacquard index. In green, you have true positive, so excellent, the model and the expert agree. In red, you have false positive. The model thinks it's fine to wait there, but the expert disagrees. And in yellow, you have false negatives. And as you can see, the scene in the center is a 0.5 Jacquard index, but it's all right. There is a lot of green. There is some red area that is quite close to a person, which can be problematic. Again, you are not respecting the proxemics social norm, but yeah. And you see that it degrades with the score accordingly. We had, before I go into the questions, we had 3 test data sets for this. First, we had 2 procedurally generated data sets, which they were also annotated by the expert. The first one was in distribution, generated with the same rules as the training data set. The second one with out of distribution parameters, different amount of people, different lobby, different elevator sizes, just to throw off a bit the model. And the last one, and most important one, was the real elevator data set. We took videos of an elevator lobby in South Korea, and we manually annotated the waiting scenes and put them in our simulator. And yeah, so the first of all was the first question was the good old Occam razor. Like, do we actually need machine learning for this thing? And luckily the answer is yes. The baseline is what I presented at the beginning, which just the average and the weighted average of the social norms, and it performs extremely poorly compared to all the other models. And as you can see here, I didn't only try the UNet at the bottom, but I also tried other more traditional machine learning approaches like random forest that it's 20 years that you don't hear about. But, and they perform all right, especially compared to the baseline. So machine learning was indeed necessary. Do the social cost map actually help? And to do so, we trained some models with some base cost maps that have all the information that is needed to create the social cost maps, but they don't have any information about the social norms. And again, we trained all the models using those two things, the two sets of cost maps. And again, the columns that are red are the one using the base map. So the social cost map that we operationalize, they help the training of the model, especially in this low data scenario. And if you pay attention to the last line of the UNet, the distance between the two columns is not so much. And here we think that the UNet has enough data, enough parameters that if we would have way more data, we would not need this. We would not need the social cost maps. The model would be able to recover the social cost maps from the expert annotations. Third question, very important. We trained only on procedurally generated content. Does it work in non-procedurally generated content? And luckily, yes. That was my first issue with this. The performances on the procedure generated content and non-procedure generated content is similar, so that's a yes. And finally, the most important question is the robot behavior socially acceptable? The short answer here is that we don't know yet. We still have to deploy the algorithm in an actual elevator scenario, run ethnography studies, and see how people interact with this. We did a bunch of things already in simulation. We had experts looking at the annotations, at the model decisions and ranking them based on their safety. We also checked if the models could recover the relative importance of norms from the expert annotations, because again, we had these two missions, the priority and the yielding, and certain norms apply to one mission and certain norms apply to the other one. And yes, the models were able to recover this relative importance, so that's great. But as I said, next step is really to deploy it and gauge the social acceptability of the whole system. And basically, going back to the questions I had at the beginning, can we get away only with positioning? Is positioning enough for this sort of scenario, or we have to add, out of necessity, verbal interaction, light interaction, non-verbal, but still communicative interaction? The other question we have is also, does it apply to other waiting and queuing scenarios? I mentioned before, we would like to try this in batch gates, corridor crossing. And one thing I really want to try is that, can we adjust the model decision by changing post-training the social cost maps? And what I mean with this is that we train the models with certain set of cost maps. And then at runtime, after training, when the robot is finally deployed, we change the weight of the cost maps, or we change the cost map itself. We make it stronger, we make it weaker. And ideally, we would like the model to adapt the decision to the new guidelines to the new norm that I just provided. And this is very preliminary work I tried last week. And it works for the proxemics, so great. You see that when I make the proxemics guideline stronger, so the penalized area are larger and the waiting area shrinks, and vice versa at the bottom. But, for example, it doesn't work at all for another social norm, like the board as fast as possible. So this is really in ongoing work. The take-home message that I want to give here is that let's not discount feature engineering, especially in HRI. I understand we are in 2024 in the era of LLM, but I believe that in HRI we often encounter this like small problem that required data that we don't have, and the data we require is quite rich. It's interactive data. And here we can really leverage knowledge that is not data, knowledge that comes from sociologists watching video of people taking the elevator and then summarizing their knowledge to me. And we can reuse knowledge, take this knowledge, input it as a prior in the models, and ideally leverage its interpretabilities I showed before. So that concludes my talk. Thanks a lot.